If you're looking to observe your network, your processes, your file systems and more using ebpf, then this episode is for you. Welcome to Is It Observable? The main objective of Is It Observable is to provide tutorials on how to observe a given technology. Today's episode is part of the Kubernetes series, but it's in fact a general observability topic. In the Kubernetes series, we already had several episodes covering several topics. So we had how to produce metrics, how to produce logs using different solutions like FluentD and FluentBit, and also how to collect events. In fact, way more. Today, this episode will be focused on a powerful technology that allows us to observe, secure, filter our network, and I'm referring to ebpf. If you enjoyed today's content, don't forget to like and subscribe to the channel. So let's see what you are going to learn out of this episode. We will start with a short introduction, then we will present the value of ebpf. We will look at what is a BPF map, then we will look at how we can build an ebpf program. We will present few solutions of the market utilizing ebpf, and like usual, we will end with the tutorial. ebpf stands for Berkeley Packet Filter. In fact, ebpf is the new version of a technology called BPF. BPF was initially created to analyze the network traffic and provide filtering capabilities. So let's go back when BPF was originally created in 1992. So at the end, it's a quite old technology. Even if at that time network traffic was much simpler than today, remember it was the rise of internet. And many engineers were already thinking of being able to analyze or filter the traffic. Let's say we want to analyze and report all the TCP communications managed by our server. So to do this, we can either modify all the code of all of our servers to log everything from our incoming connections or outgoing connections. This approach will approximately work, but it will require a lot of effort. And we would need to provide this code that we have built to all our servers of the organization. The other approach is to fork the kernel code used by our servers and update the kernel code by adding some instrumentation instruction in our kernel. Well, this is way more complex. Building kernel code is obviously very complex, and we would need to run lots of tests to fully measure the impact of the code and more. And by the way, we have to manage as well all the security patch that we would need to manage in the future as well. The kernel code provides lots of features, but it manages also all the instructions to interact with our hardware equipment. When we build our own code, we never define how we want to interact with a hardware device, a disk or a memory, for example. Our code uses predefined syscalls to interact with the hardware, so the network, the card, the disk, and so on. When we deploy our code in our environment, our code will sit in the user space. Our code will interact with a kernel that will be, at the end of the day, the bridge to the hardware of the servers. So ebpf was created to be able to inject simple programs in our kernel based on syscall events. Initially, ebpf was used for analyzing the traffic. For example, once BPF code is deployed, it will register to a network packet kernel event. We can have one program that will, for example, look at the incoming and outgoing packets. Every time a packet comes in the server, the BPF program is launched and analyze the TCP packet. In reality, several networking tools has been built with the help of BPF. For example, there's one tool that we use quite often, and it's TCP dump. BPF was also used for filtering. Let's say we want to accept packets that has a signed hash in the header of the packet. So similar to the analyze scenario, the BPF program will be launched as soon as there is an incoming packet. And once it's launched, it will look at the packet, especially at the header, if the expected value of field is there or missing. And then, depending on the results, it could drop or accept the packet. As you can understand, BPF was mainly focused at that time on networking use cases. Since kernel 3.18, an extended version of BPF has been released, providing more features. It will not only focus on packet filtering events, but to almost all kernel events. ebpf provides also a support for 64 bytes, so we can collect and store more information. A more important feature, there is a data structure that has been created to help us to store the data and exchange with our user space programs. So with the extended version of BPF, we can now improve the current feature from our kernel by adding a process that collects KPI when our kernel is managing our socket connection, process, memory, and more. The ebpf program has the ability to register to any kernel events. Once our kernel event happened, our ebpf program is triggered. So what type of events do we have? Well, there are lots of events. Events related to almost all the syscalls. So it means it could be related to the network, so open a socket, close a socket, a disk, so write, read, creation of a process, a thread, a CPU instructions, a process, some stack trace, and much more, in fact. With ebpf, we can now build programs for various use cases. Of course, the networking to analyze routes and more. There is also security to filter traffic based on specific rules and reporting any valid or blocked traffic. We also have tracing and profiling. ebpf can help us to collect detailed execution flow from the user space program to the kernel instructions. Last use case, which is in our favorite use case, in fact, it's observability. Because it's based on syscall events, we can imagine many observability use cases to report disk activities, process, CPU instructions, and more. By nature, it's more efficient because we are not required to pull for the information anymore. Our program will be launched exactly when we need to measure something. Many engineers, including Thomas Graf from Isovalent and part of the Cilium project, compare ebpf to JavaScript in our browser. As you all know, JavaScript can modify or change our page structure based on a DOM events. Well, ebpf would do the same, but with our kernel. So let's say we want to write a program that collects the number of bytes, the name of the file, the folder, when we write into a file. So first, we need to figure out the right syscall events. In our use case of writing in a file, we'd use the vfs_write event syscall. Then we can start writing our ebpf program that will be registered to the vfs_write event. Once the code is deployed, every time a vfs_write syscall is triggered, our ebpf program will be executed and will collect the right data. So the question is, we collect information from our ebpf program sitting in the kernel. How can we retrieve this information back to the data in our user space with our program? Well, for this, we have ebpf that comes with bpf map that can help us to store data in hash map, stack trace, and more. One of the major improvements provided by ebpf is in fact the bpf map. bpf map is a storage located in the kernel. to be able to access the data stored in the kernel, ebpf provides syscalls that we can use to retrieve the data stored in the BPF map. ebpf provides various types of BPF map. So here is the list of all the various BPF map. Those BPF maps has been designed for specific use cases. So BPF map underscore type underscore hash and BPF underscore map underscore type per CPU underscore hash are hash map storage. So basically key value pair storage. But BPF map per CPU hash provides a separate value slot per CPU. So we could have a hash map for each CPU. Same thing for array. So BPF map type array will provide a storage similar to an array, where we would have to define the maximum size of the array. And in the array implementation, you also have the BPF type per CPU array to store per CPU histograms of latency. BPF map type stack trace will be expected to be used to store stack traces of our programs. Therefore, building our ebpf program will need to figure out what type of BPF map do I need to use to store my data. But hash map and array are the most heavily used type. To be able to use BPF map, you will first need to declare it. And for that, we need to define the BPF map type, for sure, the max number of elements that we expect, the key size in bytes, and the value size in bytes. The kernel comes with predefined functions, allowing us from the user space to create a BPF map, to look up for a given key, create or update a key value in the map, find and delete by key, and delete a map. Writing ebpf programs sounds very complicated, and in fact, it's a bit complicated. You can go the hard way, where you write an ebpf program using a pseudo C language and compile it using the LLVM compiler to compile and get ebpf bytecode. But don't worry, there are simpler ways of building ebpf program. There's a framework named BCC that helps us to build a program using a Python library. BCC stands for BPF Compiler Collection. BCC has mainly been built for profiling and tracing feature. So here is the link to the BCC IO Advisor repository. BCC provides a set of tools built by the community and that has been initially built and created by Brendan Gregg. There's a list of predefined Python program that will help us to trace various components of the kernel. So here is a diagram with all the various tools that BCC provides. If you want to learn more about those tools and how to use it, I would definitely recommend to watch the following video. It's a Brendan Gregg presentation explaining the various toolings that he has built using BCC. If you're planning to build an ebpf program using the BCC Python library, you will have to follow a couple of steps. So first, you will have to declare a string containing your ebpf program in a C language. Then you will probably collect metrics. You will have to explain what to do with your metrics collected in the BPF map. So use also a couple of helpers to interact with the BPF map. Then you will have to register your ebpf program to a specific kernel event. When we deploy our BCC program or our ebpf program, it will go through several steps. So first, BCC will compile and build the ebpf bytecode program. The bytecode program will go through several verification steps. So first we have the ebpf verifier. So these components make sure that the program is safe and performant. Our program cannot be too complex and generate performance issues in our kernel. Therefore, it checks that it's safe enough to be executed. Then, once it's been approved, it goes into the JIT compiler that transforms the eBPF code into bytecodes. Otherwise, there are other options. You can also build eBPF program using BPF trace that provides high-level tracing language from our kernel. In fact, it's available from the kernel version 4.x. So you will build a BPF trace program that will be compiled to generate the program in bytecode or BPF bytecodes, and then it will follow the similar journey than BCC. So first the BPF verifier and then the JIT compiler. There is also a Go library, so the ebpf Go library that is available that will also help you to build eBPF program with a couple of helpers. And once you want to execute that program, it will follow the same approach. So first compile it to generate the eBPF bytecodes, and then again the eBPF verifier and the JIT compiler. eBPF program has a couple of requirements. Of course, it needs to be lightweight and reliable, but it needs to use also a set of helper functions built for eBPF to access various elements of the kernel. This set of helpers is continuously evolving, so you should check it out. But there are a couple of examples or helpers that help you to, for example, generate a random number, get the current time and date, to access an eBPF map, to get process, C group, context, and more, manipulate the network packets and forward logic. So there is plenty of various helpers that help you to do a lot of actions within the kernel. Last, an eBPF program needs to have a type. The most common types are kprobe, so it's going to be basically to collect kernel level details information. You can also have a type with uprobe to collect details from the user space. So here it's more on observability level usually. And last, you have trace points, to basically trace or stack trace. Over the last few years, lots of tools are using eBPF to extend observability, security, or networking scenario. So there's plenty of them. So we have Cilium and Humble, which provides very interesting networking and observability features for bare metal environments and also Kubernetes. You have Falco. Falco is really popular, and it's basically a security tooling that will check our runtime in Kubernetes. Pixies, I've probably heard about that project. So it's an open source observability tool for Kubernetes, relying again on eBPF. Then you have a couple of profiling solutions. So continuous profiling, so Pyroscope. So this uses the libBPF library to do some profiling. You have another solution called Parka that is continuous profiling using libBPF Go library. And then on the security side, you have Tetragon. So Tetragon is also another project from the Cilium project that provides, again, security runtime execution for Kubernetes. So we mentioned BPF trace that provides a couple of tools and functions to trace information from our kernel. In fact, it's great. There's another project called kubectl trace. So it's basically the BPF trace version, but for Kubernetes. And there's also another interesting project that I would recommend to look at. It's built by the Solo.io team. It's called Bumblebee. So it's a solution project that tries to simplify the experience when building eBPF program. The idea is to package eBPF program, distribute them into OCI images. So it's a sort of Docker image for eBPF program. There's another solution called Merge Bridge that uses eBPF to speed up our search mesh. So this one, I'm gonna personally look at it. It brings a lot of interest from my side. Kepler, this solution basically collects the power level consumptions of our Kubernetes cluster and expose the data collected into a Prometheus exporter. So if you're looking to measure how green is your cluster, your code, I think it's a great solution for that. In today's tutorial, we will use Kepler to illustrate ebpf. Kepler is deployed as a daemon set. The main part of Kepler injects ebpf programs to collect performance counters and trace points. With the help of the data collected and a model, it calculates the power consumptions. It also requires a cluster role to let Kepler convert the container ID information to a Kubernetes pod. And it also collects cgroup statistics. In this tutorial, we will deploy Kepler and its default Grafana dashboards, but we will ingest the data to build a dashboard in Dynatrace. For this tutorial, we'll need, of course, a Kubernetes cluster. We will have a Dynatrace tenant to be able to ingest the metrics that we will generate from Kepler. We will need an nginx ingress controller to expose Grafana, but also our demo application. We will deploy the Prometheus operator, but this time we won't need the default exporter, so we'll remove the node exporter and kubestate metrics. Because we're using OpenTelemetry, we'll need the OpenTelemetry operator that needs the cert manager as well. And from there, we could deploy our demo app, which is not the Hipster Shop today. We're going to use the modified version of the Hipster Shop called the OpenTelemetry demo. So it's a modified version, fully instrumented by the OpenTelemetry community. So it's a great way of illustrating OpenTelemetry. We will deploy Kepler, that comes with a daemon set, and also a service monitor to let Prometheus scrap the data. We will modify the OpenTelemetry collector pipeline to collect the metric exposed by Kepler and then send it over to Dynatrace. And at the end, we will build a Dynatrace dashboard.
Like every tutorials that we deliver at Easily Observable, there is always a GitHub repository related to this episode. So we're looking at the tutorials related to ebpf Kepler to illustrate ebpf using Kepler. So like I explained, there are a few steps to generate the cluster and so on. So I won't go through those steps. Make sure to deploy the cluster. You can use another flavor of if you don't want to use a Google Cloud, of course. Then deploy the nginx ingress controller, gets the IP address. So basically follow the steps that are described here. We need a Dynatrace tenant, so we need to start a trial. So click on this link, and if you don't have any Dynatrace tenant, don't worry. You can request for a new trial and get a tenant, and that will allow you to follow today's tutorials. So for this tutorial, we need in Dynatrace a few things. So let me go to Dynatrace, to my tenant. So first, make sure to grab the URL. So here I'm using a dev tenant, but you should have a URL with a live.dynatrace.com. So copy this https until.com because you will need it as an environment variable. The second thing that we need is to create an access token because we're going to ingest some data in Dynatrace. So click on the access token on the left menu, and then we're going to generate a new token here. And the token will be basically for traces and metrics. So we can say a data token, or name it whatever you want. But the most important is the scope that we are going to give to the token. And you can type ingest, for example, and you will see the various stuff. So in this tutorial, we use metrics and OpenTelemetry traces. So those are the two main ones that we need. So generate that token here, and then you can copy the value to use it for the next step. All right, so next, once you have done that part, deploy the OpenTelemetry operator. So it requires a cert manager. Wait until the cert manager as well probably started. That's why there's a kube wait pod. Otherwise, you will get an error when you deploy the operator, the OpenTelemetry operator, and then deploy the operator. Then, obviously, we have several pipelines here referring to Dynatrace. So make sure to apply those commands to update the various manifest files related to the OpenTelemetry collector. There are two of them, one sidecar and one as a daemon set. And then you can deploy the collector. So we will create a dedicated namespace for the collector, deploy the main collector there, and then you can deploy the demo app. And once you are there, we can go to the next steps where we're going to deploy Kepler. So let's have a look at what you should get once you arrive at that moment. So if I take my cluster here, a couple of things. If I do kubectl, as you can see, we have the cert manager because it's a requirement. We have the OpenTelemetry operator, which is another requirement for the OpenTelemetry operator. We have the Nginx ingress controller namespace for the Nginx ingress controller. We have the hotel for our collector, hotel demo for our application, demo application. And on the default namespace, what are you going to get? We will have few things, but Grafana, the operator, the Prometheus server. But as you can see, there are no exporter. We don't see the kubestat metrics. We don't see the node exporter. So those are not there because we don't need them. To deploy Kepler, very simple. We don't have to create a namespace. It's part of the manifest file from Kepler. That will create the namespace, the cluster role, the service account, daemon set, and the service, because we're going to do a service. Then we are going to deploy the service monitor. Here it is. And last, I have added the default Kepler dashboards in a config map, because with the operator, you can pick up that config map to load automatically that dashboards in Grafana. So this is the Kepler dashboards YAML file. So now if I open the Grafana dashboard, so here I get the URL here, I will connect to Grafana. If you didn't connect yet once, it's not a big deal, don't worry. It's going to ask you for the login password. So by deploying the password by default on the operator is admin and prom operator. So you can still connect it with this. So as you can see, if you go to general, you have dashboards that are coming out of the box with the operator. But here we're interested in the one that we just loaded, which is the Kepler dashboard. So that dashboard is taking some statistics over the last 24 hours. So to be able to get some metrics, you should wait a bit to see the metrics coming in Kepler and be able to be able to ingest the data in Dynatrace. I have modified the current pipeline that we have. So what I have done here to change and to allow us to collect the data is I adding the Prometheus receiver. This Prometheus receiver will have a job Kepler. That job will scrap every 3 seconds and will reach out to the service sitting in the Kepler namespace. And otherwise the same pipeline. The other difference in the pipeline is on the metric pipeline. Here I've added the Prometheus receiver, so we are collecting also Prometheus metrics, from that exporter. All right, so let's apply this one. All right, and let's have a look at the pods running. So the pods are currently restarting. So my 4 daemon set pods are running. I have put it a small prefix on the metrics. So if you go back to Dynatrace now in your tenant, I can go to the metric explorer or metrics. So metrics will be like an inventory of the metrics, and so we can start from there, and we can search for Kepler. All right, so we have already have to have Kepler, so Kepler pod dynamic energy milliseconds. So we have a couple of counters here, so it means it's already coming. So I can look at those metrics. Here we have couple of data points, and I can create a chart. So at the moment, it doesn't have much out of metrics. You can see it's quite low. You can see that we have. Let me check if there is anything interesting. Energy stats. So let's have a look at this. So here I have the total mini-core consumptions in mini-joule. So I can see that at the moment I'm consuming about 1000 millijoule for each. And if you look at the different dimensions, I can split by namespace. So it could be, I can look at the various consumptions for all the pods. So I can see that the one that consuming the most is the metric server. The other one are quite acceptable. The current usage of the energy and my node, so I can split, of course, by exported instance to see. And we have the various cluster. So they are all consuming about the same stuff. We can also add dashboards related to the pod. So we can say, for example, per the total. So there's a total energy. So I'm not doing any GPU, so it's not interesting. So I can say, look at the total energy millijoule count in total. So I can write that query and put it into, instead of that, I will put that in a graph. So I can see the total amount of consumptions for that, all the pods. And then I can, for example, split by namespace to see which namespace is consuming the most. So at the moment, it's mainly Kube Systems. The second one is my OpenTelemetry demo. So it's interesting. So I can also provide that type of feedback from a project perspective.
That's it for today's episode related to ebpf. So as you can see, today's episode was mainly an introduction to ebpf, where we explain how the technology works, how you can build your ebpf programs, and which solutions are in fact using ebpf. We did not do any coding and building ebpf programs, but that was not the purpose of today's episode. I wanted to give you a good understanding on technology, because after this episode, I'm planning to do several episodes on different technology utilizing ebpf. If you enjoyed today's content, don't forget to like and subscribe to the channel. So see you soon for another episode. Bye.